All right. So you guys probably looked at the YouTube clip and noticed that it's a little long. And I'm sorry. This, like I mentioned before in class, this is a beefy chapter. I could seriously spend a full quarter or longer just on the stuff in this chapter. Actually, a semester I could go. But we get a couple weeks, right? Really, not even a whole 2 weeks. So we're going to cover some ground in this lecture right here. So I have built in a couple pauses, right? So some places where you can kind of hit pause, go back and regroup, catch your breath, and so on. But we gotta push through this material, and I promise to give you guys time in class to process a lot of this. And we'll do a lab that goes along with it, and do lots of talking about it. But if we can at least get this stuff in note form by tomorrow, we'll be in good shape. Okay. So let's start talking about the atmosphere. All right, so our global atmosphere, right, as you guys know, is an invisible layer of gases, right? And in those gases, about 21% of the gases in our atmosphere is oxygen. About 78% is nitrogen, leaving 1% to be a mixture of things like argon, carbon dioxide, etc. Okay? So parts you guys need to remember, probably these two numbers in terms of memory. Right, knowing that we're about 78% nitrogen, 21% oxygen in the atmosphere. Okay? Now, if you look at this cool little graphic over here, by the way, it shows an increasing density as you get closer to the surface, and that kind of makes sense. Lots of people operate under this false impression that there is no matter or no mass with air. Air has mass, and that's why you can feel the wind blow. Right? That's why wind can knock trees over. All right, air has mass, and the closer you get to the Earth's surface, the more molecules of air there are, the more tightly packed they are, at least, and the more dense that air is. All right, it's also interestingly why when you go over a mountain pass or up in an airplane, your ears pop. Right, you go higher in the atmosphere, there's less air above pushing down on your ears, less pressure, and so your eardrums work to equalize that pressure. Okay. And probably one of the more important things the atmosphere does for us, you guys may or may not already know, is that it shields the Earth from some really nasty radiation the sun sends us. Right? So the sun's actually sending us all types of electromagnetic radiation. Some of it's harmless, like visible light, for example, which we use, and plants use certain wavelengths of that light. Certain wavelengths help warm us up a little bit. But some of that radiation is really nasty stuff. And the atmosphere, particularly the upper atmosphere, helps to shield us from that nasty stuff. All right, so College Board wants you guys to know the atmospheric layers, right? So we're going to go through. There are 5 of those layers. The first layer is the troposphere, and that extends between 0 and about 10,000 meters, or 10 kilometers, okay? And again, it's not like there's a line, separating the troposphere from the stratosphere. Interestingly, sometimes clouds make it look like there's a line, but there's not like a line. You can't look at a cross section of the atmosphere and see a line where the troposphere and stratosphere are necessarily, depending on actually cloud conditions. But never mind. All right. So in the troposphere, it's the only layer where we find biomass. So all living things are below the troposphere stratosphere line. Okay, it's also where all of our weather occurs. So you see these big, tall, billowing thunderstorms. They kind of tend to top out at what they call a tropopause, the top of the troposphere. Temperature decreases with altitude. That's why it gets colder when you go up in the mountains, for example. Part of the reason, at least. And most of the air molecules. So even though this troposphere way down here, it looks like a really, really thin little layer, right? Most of the air molecules are actually found in the troposphere. And again, that has to do with the fact that the air is so much more tightly packed, much denser down here. Okay, stratosphere. Now, just a heads up, guys. Hopefully, you're not writing every word you see down. Okay, for the troposphere, well, I suppose all this is good to know. But the stratosphere, right? We are talking about here, right, between the troposphere and sorry, excuse me. Yeah, sorry, right there. Between the troposphere and the mesosphere is our stratosphere. And the stratosphere, two really important things. For whatever reason, College Board likes to know about the temperature profiles. So in the troposphere, where we live, the temperature decreases with altitude. For whatever reason, in the stratosphere, temperature increases with altitude. Okay? Probably more important to remember, though, is the fact that the ozone layer that we've probably heard of, where it absorbs some of the ultraviolet B and C radiation, is found right there in the stratosphere. Okay, and mesosphere, not a lot going on there. All right, it is a layer where temperature, again, decreases with altitude. All right, but in terms of other things, there's not much going on. Now, do you guys need to remember or know these numbers? I don't think I've ever seen an actual AP test question that specific. Now, we really need to know the 5 layers and the order from surface upward or top downward. Yes. But you guys need to remember the actual distances? No. All right. Thermosphere. All right. Now, thermosphere is kind of a cool layer. First of all, it's really, really hot up there. Now, interestingly, if I was to go up into the thermosphere, which that's not a very welcoming place, by the way, because we now have exposure to all kinds of nasty solar radiation. But if I was to go up there and stick my hand out, there, it wouldn't feel hot necessarily. And the reason for that is the air is so thin that my hand would come into contact with very few air molecules. So the air molecules might be really hot. Not very many of them would actually touch me, so it wouldn't necessarily feel hot. That and the pressure would be so low that my blood might start boiling or something like that. So bad news. I don't want to go up in the thermosphere. But okay, what's going on up here? We have gases in the thin air absorb X-rays and shortwave ultraviolet radiation. Okay, that's stuff that would do some serious damage to us with long-term exposure. And it's also cool. I don't know if you guys have ever seen it. Is the northern lights or aurora borealis and their counterpart in the southern hemisphere. That's actually where that's occurring. There's some interesting charged particles that come at us from solar flares from the sun, right? And the Earth's magnetism actually deflects those particles north or south, okay, based on magnetism. And as they go screaming through our thermosphere, it reacts with some of the ions in the upper atmosphere, and part of that reaction releases light. So you get these really cool ribbons of light that kind of go streaming across the upper atmosphere there. And if you ever get a chance to see it, occasionally you'll actually be able to see them down here in Washington. I think in my lifetime I've seen them maybe 3 times. I remember the first time I saw them, I didn't know what the heck was going on. I thought some alien invasion was happening, but it's pretty awesome. All right, and then we have our exosphere. Now, it's not like all of a sudden you're in the atmosphere and then you're in outer space. So with the exosphere, it's just kind of where we still have some atmospheric molecules hanging out, maybe enough to still call it part of the atmosphere. But essentially, it just slowly thins and thins until you kind of get up into outer space. A lot of our satellites that kind of have the lower Earth orbit hang out in that exosphere. All right. Deep breath. Okay, moving on to climate. This one makes me happy to talk about. This is when we start talking about these global and Earth processes. This is my time to shine because this is what I studied in college, or most closely. Of course, I studied some chemistry and I took some environmental classes, but Earth science specifically is one of my favorite things to teach. Okay, so when we talk about climate, right, we are talking about average conditions, and the 2 most important factors are temperatures and the amount of precipitation. Okay, that's an important thing to remember. Climate describes the temperatures and precipitation in an area on average over long periods of time. Okay, so regional climate. So climate in the Pacific Northwest, for example, or Eastern Washington versus Western Washington even, right, is a function of really 3 things. There's other things too, These are our three main factors. Number one is latitude, right, which is going to affect the amount and the intensity of sunlight that we get. Number two, proximity to large bodies of water. We have a lab that will explore that effect here just tomorrow, okay? And topography, again, mountains, right, and altitude, and which side of the mountains you live on relative to wind patterns, right, also affect the amount of type of weather. And that's what actually, part of what explains, the Eastern Washington versus Western Washington climate difference, right? Why is Western Washington so much wetter? It has to do with topography and proximity to water. But we'll get to that in just a little bit. All right. So when, first of all, understanding climate, we're going to kind of look at the effect of latitude. And the effect of latitude is really a function of sunlight. All right. But let's start big picture. Let's look at the whole globe. Then we'll kind of zoom in on different latitudes here shortly. Okay? So with sunlight, right, we have our incoming solar radiation from the sun, which is relatively constant. There are some weird little cycles with how bright the sun is, but it doesn't change very much in yours or my lifetime. Right? So we're going to say that remains relatively constant, that incoming solar radiation, averaged over the whole globe. Okay, so of that incoming solar radiation, we're starting, that's our 100%. Okay, about 69% of that incoming radiation is absorbed either by clouds or the atmosphere or the ocean or the Earth's surface. Some sort of absorption occurs, okay, for 69% of that. 31% is directly reflected back to space. So it doesn't really heat anything up, at least not down at our surface. Okay, so only about 69% is actually being absorbed. 31% gets directly reflected. Okay, so what does the absorbing again? Right, the ground absorbs some, clouds absorb some, molecules and dust in the atmosphere absorb some of that sunlight. Okay, so that's part of our heat budget. So we're really only operating with about 69% of the incoming solar radiation. Okay, now, over time, okay, 100% of the incoming solar radiation is radiated back into space, all right? And why this is important to understand now is it's part of our Earth's equilibrium, so this dynamic equilibrium that keeps popping its head back up, this fundamental principle, right? Is in terms of heat and the temperature of the Earth, it relies on this one principle, right? If you average over the entire planet, okay, our average surface temperatures are about 15 degrees Celsius or 59 degrees Fahrenheit. And that's approximate, and that's the surface temperature can fluctuate with things like El Nino and La Nina cycles and so on, which creates a messy picture that we'll talk about later. But if we just kind of look long term, broad terms, averaged over the whole globe, right? At any given time of year, and any given year, if you could average the Earth's surface temperatures, it'd be about 59 degrees Fahrenheit. And that would take into account, of course, places where it's really hot, but likewise their counterparts, places where it's really cold. Average comes out to that. All right? Now, of that incoming solar radiation, says, 100% of it's radiated back into space. I suppose you could argue that small amounts of that radiation does get locked up in biomass, some of that energy itself, because not everything decomposes. So for example, our fossil fuels are stored solar radiation from a really long time ago. All right. So reflection of the radiation. So immediate reflection is about 31% of the sunlight. Okay. Albedo, really important term, both this chapter and when we start talking about global climate change. So albedo refers to how reflective a surface is, right? So clouds actually have relatively high albedo, and so when there's cloud cover, we reflect a lot of sunlight back into space. But cloudy days aren't as hot as sunny days often, okay? So dark colors have a low albedo. So low albedo means low reflection, high absorption. Okay, so if something has a low albedo, that means it's going to absorb more energy and reflect less. All right, so light colors, things that are white, right, as you guys all know, have a high albedo. So high albedo means high reflection, low absorption. Okay, so things like glaciers and our big ice caps on the poles, right? They're reflecting a lot of energy directly back to space. Now, the primary reason our north and south pole are cold has to do with sunlight, but the fact that they also have a really high albedo helps to keep them cool. It's an interesting feedback mechanism. Okay, positive feedback, by the way. All right, so this albedo refers to how reflective a surface is based essentially on its color. All right, so things with light colors have a high albedo, which means they reflect a lot of light right back to space. Things that are dark in color have a low albedo, which means they absorb a lot of that energy from the sunlight. Okay, so in terms of absorption, right, so we're talking about things that absorb solar energy and then heat up as a result. All right, so 49% of that 69% is absorption by the Earth's surface. Now we're talking about the land surface and the ocean surface. Okay, 17% is absorbed by the atmosphere. Certain gases are responsible for that absorption. We call those greenhouse gases, by the way, and dust particles absorb some of that energy. Clouds, interestingly, while they do reflect some light, they actually help to trap some of the energy that's absorbed beneath them and keep them in the atmosphere. Okay, but it is worth pointing out that all of that absorbed energy will eventually radiate back into space. So it's not going to be reflected, but it radiates. So just when something heats up, you can feel the heat radiating out, right? So when our Earth heats up, it radiates back to space. Now, the Earth's temperature, right, its current temperature, around 59 degrees Fahrenheit or 15 degrees Celsius, is that equilibrium temperature, right? And so we've kind of reached a point where the incoming solar radiation is equal to the outgoing radiation, and so we stay a relatively constant temperature when averaged over the entire globe at any given time. I'm not talking about our seasonal fluctuations, because when we start getting colder, the southern hemisphere starts getting warmer, everything stays in this sort of nice equilibrium type balance, right? Now it's dynamic. It's not perfectly, it's never going to be exact. Well, I shouldn't say never. If you were to take the global average temperature right now, for example, it might not necessarily be 59 degrees Fahrenheit. It just stays in this kind of range around 59 degrees Fahrenheit. Okay? So, what I want you to do right now, we're almost 20 minutes in. Holy cow, this is going to be long. All right? This would be a good time to pause. Look back over your notes so far and highlight key information. All right? A couple things you ought to be able to do. One, we just talked about, explain why the Earth remains, on average, around 59 degrees Fahrenheit. Okay? Why is it that any time of the year, if we took the overall average temperature of the Earth, why does it remain around 59 degrees Fahrenheit? Okay? And you ought to be able to identify the layers of the atmosphere correctly, right? I've actually made mistakes before teaching this and given people the wrong order. Look at your book. The notes are correct this time, okay? And most importantly, where does weather occur? Where do living things live? Which layer? And then, of course, where's that ozone layer? Which layer is that in? So things to go back. So take a moment, hit pause, go back and process what you've done so far. You just need to trust me. Do it. Did you? Did you? Did you? All right. Moving on. Latitude. All right. So we're going to zoom in on smaller portions of the Earth now. We kind of went global there, looking at everything on a global scale. We're going to zoom in on different parts of the Earth and how they behave due to the amount of sunlight they get, which is due large part to their latitude. Okay? So latitude are these horizontal lines you see in this diagram here, right? So those lines, of course, don't actually exist. They are imaginary lines, but they measure the degrees north and south of our equator. So equator is this imaginary line down the center of the Earth. Now you'll notice right now that we're showing the Earth straight up and down on its axis. You, of course, know that it's tilted about 23.5 degrees on its axis, which will be important to us in a little bit. But for now, we're going to pretend it's just sitting straight on an axis. All right, so sunlight distribution. So incoming solar radiation, right? As it hits the actual surface of the Earth, because the Earth is round, right? Near the equator, right? We get pretty direct sunlight, all right? And so what we're seeing here is certain amounts of solar radiation hitting the surface, right, in a direct manner. Now, as we get further from that equator, so if we go down and look at this line, a certain unit of sunlight, right, hits 1,000 kilometers. If we go further toward the equator, the same amount of sunlight, so we look at this band right here, okay, is the same width as that band. But as it hits the actual surface of the Earth, rather than distributing over 1,000 kilometers, it's distributed over 2,000 kilometers. So it's essentially the same amount of energy as trying to heat up twice as much space. All right, and that's just because the sunlight is less direct. It kind of gets spread out, and because it's more spread out, it's less able to heat, right? Because you kind of picture it as putting a light bulb in a closet, right? One light bulb in a closet heats up or lights up the closet just fine. One light bulb in a larger room is going to be less able to light things up. Okay? It's the same thing with our heat budget over surface area. 1 unit of light heats 1 unit of surface area at the equator. 1 unit of light heats 2 units of surface area closer to the poles. So we're going to get less warming. Okay? That's a really important fundamental in what we're talking about here. Okay? So this diagram kind of shows the same thing at various latitudes. So this would be like the equator. This would be like where we are here in Walla Walla. We're just above that 45-degree north latitude line. And this would put us up somewhere, you know, like in Alaska or something like that. Okay? So when we look at temperature profiles at different parts of the Earth, right, we notice that the profile changes based on latitude. So if we go to London, England, for example, 52 degrees north, they're a little farther north than we are here in Walla Walla. All right? If we look at their temperatures over the year, we see that certain months of the year, like January, November, December, we're getting a small amount of radiation, and therefore our temperatures aren't very high. And as we go to June, July, August, what we call our summer months here in the Northern Hemisphere, we see a large amount of radiation. Relative amount of radiation. Okay? Now if we go to Brazil, Brazil's right on the equator. What do you notice about their radiation budget over the year compared to London? In London, we see a big change between our winter months and our summer months. In Brazil, we see it remaining relatively constant. It's not exactly constant, but relatively constant. Okay? Now, let's go south of the equator about 30 degrees to Bulawayo, Zimbabwe, right? We see a reverse profile from what we see in the Northern Hemisphere. Again, that's their seasons are opposite of ours because they're in the Southern Hemisphere, right? And this is something you guys should understand. You should have had enough earth science in middle school to get this. But first of all, when we take into account this tilt, right? So way back here, we are looking at things being directly on its axis, right? So no tilt, right? So if there was no tilt, by the way, we wouldn't have seasons. We'd just be on average cooler than the equator is, all right? Now, because we are tilted, this profile right here that we see changes, right? So we are 45 degrees north of the equator, and if we were not tilted on our axis, we would get our sunlight at 45 degrees. But in fact, in the summertime, we get more like this, right? And in our wintertime, we end up more like that. And that's what causes those seasonal fluctuations, okay? but it's that tilt on its axis. It has nothing to do with how close or far we are from the sun. It doesn't really change appreciably due to our tilt. Our seasons are due to how direct our sunlight is, right? So in our summertime, right, the directness of the sun's rays is more similar to the equator. In our wintertime, we're more similar to the poles. And that's why we get colder in the winter and warmer in the summertime. But notice, of course, that our winter here in the northern hemisphere is the summer there in the southern hemisphere. All right, so 25 minutes in. Let's pause again. Go back and highlight key information. Things you ought to be able to do is to describe the relationship between latitude, surface area, and solar intensity. Okay? The second thing you ought to be able to do is describe the causes of seasonal fluctuations. Again, has to do with latitude, surface area, and solar intensity, and how that has changed throughout the year due to the tilt of the Earth's axis. So again, take a moment, hit pause, go back over your notes. I know we're getting long. Maybe we'll grab some popcorn, grab some coffee, something to keep you awake. All right? Take a break, watch an episode of something stupid on TV. I don't know. But take a moment, look back over your notes, take a moment to give your brain a rest. We've got 1/3 of our show to go here, okay? All right. Hopefully you took a moment to pause. But we're 26 minutes in. We're on our final bit here. So, a little bit more about latitude. So, the last piece that we needed to plug in, and I wanted to put this all kind of in one slideshow because it all fits together, and I didn't want to spread it out over a weekend or something like that, is, if we look at the radiation budget at the equator, right, we're getting a constant surplus, right, throughout the year. Now, thermodynamics tells us if we're putting surplus energy into a system, it's going to continue to heat up until it reaches an equilibrium temperature. So if the equator is at a constant surplus, theoretically it should be constantly heating up. Now, likewise, at our poles, we see a constant deficit. So thermodynamics then says that we should be continuously cooling off over time. We get a deficit. So why doesn't the equator continuously heat up, and why doesn't the poles continuously cool off? All right, that doesn't actually happen. We would have some uninhabitable temperatures over much of the Earth if that was actually the case. All right, and so what we need to understand next then is the reasoning behind why that happens, and it has to do with the fact that, hey, our air at the equator doesn't just sit there. It moves, right? And as the air moves, once it heats up, it distributes that energy to different parts of the surface, right? So this is what we call atmospheric circulation. The atmosphere is a fluid, right? And fluids can move around. And the heat can cause differences in density, and that can cause the air to get pushed to areas of high and low pressure and stuff like that. So that's this next bit. So near the equator, right, where we get our most direct sunlight year-round, all right, the warm air at the surface is heated up, and the heating air causes it to become less dense, and therefore it's kind of forced upward, right? Saying warm air rises, it's actually pushed up, so it looks like it rises, all right? Now, as that air rises in the atmosphere, though, there's a process called adiabatic cooling, which causes the air to cool back off again, which makes the air denser and then sinks back to the surface, right? So this is what we call a convection current, right? Convection, right? So we get warming at the surface, right? That causes a decrease in density. So the low density air is forced upward, right? As the air is forced upward, the adiabatic process cools it off again, which makes it more dense, which causes it then to sink, right? And that creates these little atmospheric cycles called convection currents, right? So at the equator, we get this rising air. If we go 30 degrees north and south, we see the air sinking again. So this is like the equator here, 30 degrees north and 30 degrees south or something like that. Okay? We have that air sinking back down. It actually occurs at higher latitudes as well. We'll show that in just a second. All right? And so we get these wind patterns partly due to these what they call Hadley cells or convection currents. Okay? So, again, where do we have rising air? Here. And then we have it again here and here. All right? So the rising air we see at the equator and then again at 60 north and 60 degrees south, okay, are part of these Hadley cell systems. All right? And then at 30 degrees north and south, we get sinking air, and then again at the poles. Okay, so rising air at the equator, 60 north and south, sinking air at 30 degrees north and south, and at the poles. Okay? So, rising air versus sinking air, and what that means in terms of climate, particularly precipitation patterns. Rising air tends to seed cloud formation. Okay? And so, areas in general, areas with rising air, so the equator and then 60 degrees north and south, they tend to correlate well with precipitation. Right? We tend to get lots of precipitation in our Hadley cell areas where we have the rising air. Okay, sinking air, on the other hand, it warms and dries the air. Right? So our global desert distribution, some of our really big deserts globally are found, right, at 30 degrees north and 30 degrees south. Okay, so if you look at kind of a picture of the globe, we see these brown bands, right, that circulate the globe at both 30 degrees north and south. Now, interestingly, Antarctica and our extreme northern parts, we call tundra. Tundra is also really, really dry. It's also a desert. It's just a really cold desert as opposed to a hot desert. Okay? So where we have sinking air, right, tend to be dry. Where we have rising air, we tend to be wet. Okay? Now, this is a overgeneralization, but it's going to work well for us on average conditions and for now. Okay? So, prevailing winds. All right. Almost done here, folks. Almost done. So, when you look at parts of the globe, in terms of latitude, you get these prevailing wind directions. So, up here, we are between 30 and 60 degrees north here in Walla Walla, right? So, Walla Walla's not shown on this map, but this is our band right here. Okay? The winds are called westerlies, and they tend to come from the southwest. So much of the weather patterns that we get here in Walla Walla come from over the Pacific Ocean, right? So air travels from the west to the east, right? And we call those westerlies. Okay? So much of our weather comes from our southwest area. Okay? Along the equator, so between 30 degrees north and 30 degrees south, we get what are called trade winds, and they tend to blow from the east. All right? And then, again, we get some more westerlies in a similar latitude to us, but in the South Pole. And then at the poles, we get what are called polar easterlies. Okay? Now, the reason these wind patterns happen. So first of all, winds blow from high to low pressure. So wherever there's high pressure, it's going to push air away, and it's going to push the air toward places of low pressure. So notice our arrows are pointing toward our low pressure areas. And where do we have low pressure? You should notice that that low pressure comes from rising air. Right? So places where we have rising air are places where we have low pressure. Okay, and the arrows, the wind tends to blow toward low pressure. This would be something you really need to remember. Okay, wind blows from high to low pressure. And so if we have an area of low pressure, that's where the air is going to move toward. Okay? So we see these high versus low. So air is blowing away from the high pressure bands toward the low pressure bands. All right. Now, why are the arrows tilted? So, for example, why is my wind direction not straight toward the equator? All right. Now, this is probably our most abstract idea coming up. And it's something called the Coriolis Effect. And it has to do with rotational velocity at different parts of the globe. This is definitely something I'm going to have to talk about some more when you get to class. I'll do my best to explain this, but it's fairly abstract. Okay? So, the Earth rotates from eastward. Okay? So what you have to understand, so if we're looking at the globe here, for example, we are rotating this direction. Okay? Alright. So, if I am standing at the equator, right, at any given moment. So let's say I'm standing right here at the equator. And you are standing up here much farther north. Now, your day is 24 hours. My day is 24 hours. But who is traveling a farther distance in that 24-hour period? Okay? In reality, yes, we're both doing one rotation on the axis, but your diameter of this circle right here, so you got to remember this line is actually a circle, right, that goes around the Earth right here. The diameter of your circle is less than the diameter of my circle. So I'm actually traveling a farther distance in a 24-hour period. And if I'm traveling a farther distance in the same amount of time, that means the equator, the surface of the equator has a higher velocity than the surface where you're standing up here at 60 degrees north. Okay? So what that means is essentially the air above 30 degrees south and 30 degrees north, for example, is part of that rotation, and it's rotating at a slower speed than the equator. All right? And so as the Earth rotates, so as I'm rotating here on my equatorial line, my imaginary line, the air that's moving toward me is rotating more slowly than the location where I'm standing, and that the effect looks like this. If I could color the air and actually see the air moving, it would kind of do this little rotation pattern. So these lines really aren't straight. They actually kind of go like this. They veer off. Okay? Now, the best way I can try to explain this is with a merry-go-round. Alright? So if we could picture the North Pole, for example, is like the center of a merry-go-round. So if I'm standing at the center of a merry-go-round, I'm just going to kind of rotate in a little circle. Right? If I go farther out on that merry-go-round, we're doing one rotation in the same amount of time, but the person on the outside of that merry-go-round is traveling a larger distance. So out here is more distance than in here. Okay? So if we're traveling this direction, right? If I was to try to pass a ball to you, right, or just roll it across the merry-go-round, right, the ball would appear to this person here to curve off this way. Now, in reality, that ball went in a straight line. This person is just moving. But to this person, it would look like the ball veers off. Okay? So that is actually what we have happening to our air on the Earth, right? So if air is flowing from the pole toward 60 degrees south, for example, right, it's going to appear like the air veers off. Okay? In reality, the air is going in a straight line as the Earth is moving, kind of. Okay? Now, like I said, I'm going to have to touch on this again, okay, when we get back to class. But the net result, right, the arrows are pointing toward our low pressure or rising air, right? Okay, so notice how the arrows pointing toward it. Because the Earth's also rotating and we have differences in what we call rotational velocity. Okay, things get pushed to the right in the northern hemisphere and left in the southern hemisphere. Now again, in class, I'm going to have to talk about some nuances there and how to actually picture the way that occurs. Okay, but answering our initial question, why are our arrows not pointing straight toward our low pressure areas? It's because of the Coriolis effect. Things get veered to the right in the northern hemisphere, left in the southern hemisphere.